Alright, so we have been talking about exponential functions, and today we are going to study something brand new to you anyway, and those are logarithmic functions. So a couple learning goals: we need to be able to write logarithms in exponential form, and vice versa, we need to be able to write exponentials in logarithmic form. We need to be able to simplify and evaluate logarithms with and without technology. So we want to be able to press the buttons on our calculator, but you also have to know how to do some things by hand as well. And then finally, we want to be able to find the inverse of a logarithmic function. So I want you to understand the purpose of logarithms because it sounds fancy, and most of what sounds fancy, people think that we don't really need. But there is a purpose to these logarithms. Earlier in this unit, the first time was in your 8-2 example 3C. We solved this equation by guessing and checking. We wanted to know how long it was going to take. And so because we had no way to get this t down when we're solving for it as a variable, we had to just guess and check and come up with the two numbers that surrounded the 0.3913, and that's the only way to do it algebraically. We could do it graphically by putting this in your y1 and this in your y2 and using your intersect feature, but algebraically all we could do was guess and check. This allowed us to find an approximate answer. Most of us prefer an exact answer rather than a guess, especially in situations where we're trying to get down to small amounts, when we're getting down to dollars and cents or other things where small rounding differences make a difference. So we need a way to get variables down from what I call the prison tower here. So with the radicals, we were breaking out of prison, and here we've got a prison tower that we need to get down from. So in order to get variables down from that tower when they are an exponent, we're going to do that with our very smart sounding word, which is logarithm. And we call them logs for short. So just like subtraction is the inverse operation for addition, logarithm is the inverse operation of an exponential. So if you are trying to undo an exponential, then you need to take the logarithm. If you are trying to undo a logarithm, then you would switch it to exponential. Now, what we have here, this is the logarithm of y with base b that we have here. And we're saying that equals x if and only if b to the x power equals y. This is the whole basis of logarithms. Now, we're saying log of y with base b is x if b to the x power equals y. So we convert from one form to another, and the process we use, I call it the swoop. I'm sure there are lots of people that call it something different, but what we're going to do is we're going to start with this log, same exact thing that we saw right above. But here's what I mean by the swoop. When you start a swoop, you're going to start with the base of the logarithm. So we're going to start here, and we are going to swoop across the equal sign to pick up the x as our exponent. And when we switch back, we put the equal sign in. So b to the x, the second time we come around the equals, we put it in, equals y. And notice that's exactly what it says here. So we call it a swoop because we're swooping around, picking up the exponent, bringing the equals back, and then finally getting our y. So that's what we call the swoop. Now, very important that you sound intelligent and that you use the correct terminology so that I know what you're talking about and anyone else you're asking a question to or clarifying things with knows what you're talking about. So when we read these, we don't have to say logarithm of y with base b every time because that sounds intelligent but really nerdy and over the top. So for short, we are going to call that log base b of y. So the base is always little here. It's like a subscript. So log base b of y. So example 1, rewrite the equation in exponential form. You can practice your sounding intelligent with reading right here and read these first two to yourself each time, and then you can check them. So when you read this, this should be log base 3 of 9. So to rewrite in exponential form, all that is our swoop. So start with the base, swoop around to get the exponent, pick up the equals on the way back, and let it equal 9. So 3 squared equals 9 is the exponential equivalent of log base 3 of 9 equaling 2. So practice your intelligent reading here. Hopefully you said log base 8 of 1. So now to rewrite in an exponential form, start with our base, swoop around to get the exponent, then back to pick up my equals and my other number. So 8 to the 0 equals 1. And then finally, log base 5 of 1/25 would be 5 to the negative second power equals 1/25. All right, so we can also use our swoop method to evaluate expressions without a calculator and then eventually to solve equations. And many of these things we can't actually do on the calculator. These, in example 2, we can. Evaluate the expression without using a calculator. Some of these we can do in the calculator, but these ones we're doing without. When we are doing it without, what we're doing is we're asking ourselves, what does that equal? So when we're asking, that's what we're trying to find out. We're saying that equals x. X is our unknown. So in order to find out, I can convert with my swoop. 2 to the x equals 128. And that's going to help me because no one, just off the top of their head, when you say, what's log base 2 of 128, can come up with the answer. So 2 to the x equals 128, however, we can come up with an answer. Now, when it says without using a calculator, if you don't know what power of 2 equals 128, that's okay. You can use a calculator to help you come up with that. But we're not pressing this in. You have to have work to show. So I know that 2 to the 5th is 32, so 2 to the 6th is 64. So that means I know that this is x equals 7. But if you don't, you can keep trying powers of 2 until you get the right one. So evaluate the expression without a calculator. We don't need the x equals in our final answer because there really wasn't an x in the problem. So 7 is our answer. All right, let's try again here. This next one, 1/4 to what power equals 256? Because the answer to that question is going to tell us what log base 1/4 of 256 is. Now, I picked this one on purpose because you have a fractional base. When you have a fractional base, there should be some kind of flashing red light that goes off in your head that is going to tell you that you're probably going to have a negative exponent. Now, not always, because if this is a fraction 2, it'll be a positive exponent. But a lot of the times when you have a fractional base, you have a negative exponent because we have to flip it. Because you can easily find out what power of 4 is 256, but this is 1/4. So if you can answer what power of 4 is 256, then we just make that number negative. So 4 to what power equals 256 would be 4. 4 to the 4th equals 256. So that means that if I use the negative 4th power, that would give me 256 from a base of 1/4. All right, last one. Same idea. This one looks harder because it's got like a second exponent there, but this one is actually easier. 2 to the x equals 2 to the 0.72. Oh, look at that. They have the same base. They're set equal. That means the exponents have to be equal. So x equals 0.72. So those ones are actually easier, even though they look harder. All right, now we're going to learn how to punch the buttons in on your calculator. There are two types of logarithms that we're going to learn about. The common logarithm that is base 10, and on your calculator, that is the button that actually says log. So if you're looking for that button, if you don't have your graphing calculator, go get it because you need to make sure you know how to press these in. But the log button is just to the left of your 7 key. So that's the button we're going to look for. Then the other button, the other type of logarithm, is the natural logarithm. And that has base E. So natural log is the LN button, which is directly underneath the log button. So when we learned the e to the x functions and we called those natural base, that's why these are called natural logs, because they have the natural base as their base. So example 3, super easy. All you're doing is pressing the buttons on your calculator. So you're pressing log 7, enter, and then it says to round to 3 decimal places, so 0.845. And again, natural log is how we read that. Natural log of 0.25, press it in. You should get negative 1.386 on 3 decimal places. Now, due to the definition of logarithm, because a logarithm is the inverse of an exponential, we can conclude that these two are inverses of one another. So, because they are inverses of one another, you should know that their compositions should equal something. We've studied what inverse functions do before. So if I did the composition of f of g of x using these functions, again, remember that a composition, this is good review here, all it does, the outside function here, f, so this one right here, I take the x out, so I put log base b, and in place of the x, I put the other inside function, so in this case, b of x. So that's how we would write it. We should know what this equals, because if these are inverses, which we already know that they are, the compositions of inverses, remember, always equal x. So this brings us to a very important property, and that is that when the base of the logarithm and the base of an exponent match, it just cancels that whole log part out. And whatever the exponent is, that's what it simplifies to. So this can save us a lot of time, less swooping that we have to do, so to speak. So let's look at g of f of x, because that might give us another property. So g is the outside function, so right here, g. So b to the, remember that when I'm doing a composition, I replace x. So in place of x, I'm putting in this whole function, log base b of x. Again, if they're inverses, which they are, that means their composition should equal x. So again, new property that we've discovered here, when I've got an exponent that has a log, if the base of the exponent and the base of the log match, the whole thing simplifies to whatever this is. And it's not always x, because we're going to have ones where we've got something like this, log base b of b. Well, that looks just like this. So whatever the exponent was is the answer. So here the exponent isn't written, which means it's 1, so the answer is 1. Log base b of 1 is 0. Let me show you why. Because this is the same thing. 1 is the same as b to the 0 power. So again, using this property here, whatever this exponent was is what it simplifies to. And that exponent was 0. And those are going to come back again when we solve equations. So it's important that you know these properties that we just discovered. All right, so we're going to use those properties here to simplify the expression. So this first one is tricky. And it's not going to be tricky, hopefully, once I tell you this one time. But when we look at our two types of logarithms, it says the common logarithm is base 10. So that means if no base is written, it is base 10, the common log. So here, on this log exponent, I don't have a base written, which means it's understood to be 10. So I've got 10 log base 10 of x. This property is the same as this one. The base of the log and the base of the power match, which means it just simplifies to whatever this is. So again, it happens to be x in this case, but if I had 4x written here, the answer would be 4x. So that's x. Here it seems like I can't use the property. But 125 is a power of this base 5. So we need to rewrite it in order to simplify. So always write things in a smaller base if you can. So 125 we could rewrite as 5 to the third. So we are going to rewrite that. Log base 5 of 5 to the third, and then don't forget it had a power of x, so power of a power, they multiply. Now that we write it in the smaller base, we see this base and this base match, so it simplifies to whatever the exponent was. So again, I always have people every year who just always write x whenever they're doing this because that's how we discovered the property. But again, that was to show us that it simplifies to whatever that is. So in this case, it's 3x. All right, last examples. Find the inverse of the function. So we have found inverses in the last unit. And we did an activity where we discovered some of their properties. Remember that the first step is to switch x and y. Second step is to solve for y. So here I'm going to switch x and y. X equals log base 8 of y. Now, here because I have a logarithm, the way that I'm going to solve this for y is to undo the log, which means I need to do my swoop. So start with the base, which is 8, and here I'm swooping to the left, pick up the exponent, so 8 to the x equals y. And that's it. Over here, switch x and y first. Now, when I go to swoop, I might get confused. There's no base here. go back up here, the natural logarithm with base e. So even though it's not written, you have to know it's there. So e to the x equals y minus 3. So e to the x equals y minus 3. Here we're not done in one step like we were on the other one. To get y alone, I need to add 3 to both sides. These are obviously not like terms, so it's y equals e to the x plus 3. Very last one. I would like for you to try it and then unpause to check. All right, so first hopefully you switched x and y. X equals log base 2/5 of y. So in order to undo that logarithm, I need to start with the base and swoop. So 2/5 to the x equals y. And here, there's nothing else with y, so that is the answer. And that is it for today.